So, as with all objects and their associated reference variables, if you assign one array reference variable to another array reference variable, both array reference variables then point to the same array object. So, what's the problem with this scenario? Well, you should remember from CS 151 that if we had two car objects and we referenced them or made them reference the same object, that could create problems if we were trying to change the color of one of them, right? So what's wrong with this code right here if the goal is to make a copy of array 1? You're not actually making a copy. You're just setting array 2, the array 2 variable, to point to the same array, right? This is pointing to this array, and this is pointing to that array. The same thing that's going on up here, right? So you got to be very careful with that. So just like the attributes of a class object, when you make a copy of an array, you'll want the copy and the original to point to different array objects. And to do that, you assign array elements one at a time. For example, suppose you use arrays to hold stores' prices, one array for each month's prices, right? So kind of like a table like this. And you'd like to copy January's price array into February's price array. How would you do that? Well, let's look at an example to see how we would do it. In this case, we're going to turn to the array copy class. And here you can see we've got two double arrays, one called prices January and one called prices February. And here we are initializing January's. And then here we are creating a new array using the length of January's to set our size. And then we are going to iterate through each of the elements in the January array and assign it to the corresponding array in February, or the corresponding element in the February array. And then we override one of the prices right there. And then we're going to simply go through and print out the prices for both January and February. So let's go ahead and run it. And there you can see it, it printed out January and February using our lovely printf command. And everything's hunky-dory. So that's how you would go through and do it. You do a element by element assignment operation to copy all the internal values over. Remember, you can't just set prices February equal to prices January, because that's going to make them point to the same array, and any changes you make are going to affect both of them. So histograms are an example of where an array is useful. So let's take a look. A histogram is a graph that displays quantities for a large set of categories. It indicates category quantities with bars. So shorter bars equate to smaller quantities and larger bars equate to larger quantities. For example, this histogram here shows the probability of dying by age 5 per 1,000 live births, right? So you can see here that Europe is actually doing really well and America is not so bad. Africa not doing so hot. You know, they're up here at 182 deaths per live birth. So this is an example of how you can use a histogram to display information. So what does this have to do with arrays? Well, let's take a look at another example. Suppose you have 3 coins where you want to flip all 3, and you're curious about how likely it is you're going to get 0, 1, 2, 3, or 0 through 3 heads, right? You want to record the frequency distribution of the number of heads per each flip. So what would we do? Well, we'd write a main method that simulates throwing the 3 coins 1,000,000 times. And then we'd print the simulation results in the form of a histogram, right? So for each of the 4 cases, 0, 1, 2, 3, or 4, we would print a bar that represents the number of times that the case occurred. And to mimic a bar, we're just going to print asterisks, where each asterisk represents 1% of the total number of simulation iterations, right? Because we don't want to print, if we're doing it 1,000,000 times and we figure an even distribution, well, that's going to be, 250,000 per. So we don't want to do 25, 250,000 asterisks. That would just be ridiculous. So we want to, have it represent multiple. So let's take a look at how we're going to do that. The output will look like this, right? So the number of times each head count occurred. Here you can see 0, 1, 2, 3, and each of these asterisks represents 1% of a million. All right. So let's think about the problem. How could we design it? Well, for starters, we could use a 4-element array to keep track of the number of times that each head count occurred. So, I mean, this lends itself right here, if you think about it. If we make this a frequency array, then it's simply we're indexing 0, we're indexing 1, and we're indexing 2 and 3, right? So that worked out quite nice. The frequency 0 element holds the number of that no heads were flipped, and the third one, it's all 3. For each element, we refer to this as a bin. And that's actually something that occurs in statistics, and you were talking about histograms. You talk about the bin size and the binning. So that's something that translates over into statistics. But after each simulation iteration, we would add 1 to the appropriate bin, right? So if we flipped all 3 coins and they all turned up heads, then we would increment the value of frequency 3 by 1, right? So this is the actual raw count. So this happened this many times. One head happened 374,759 times, right? So that's kind of how it would work, right? So what are some tips that we could do? Well, so like we discussed, we make an array of size 4, and that's going to hold our different frequency bins, and we increment each one for how many coin heads we're showing. So let's go ahead and take a look at this. So if we run it, here, let's start with that fresh one. If we run it, we see that we ran this and we got that many zeros. We got this many single flip of heads. And this one we got 2 heads, and this one we got 3 heads. And you can see our asterisks form a nice little bar graph of the distribution of those things. So we can see that 1 and 2 was pretty common. All 3 was just about as rare as a 0 flip. And you can see that this is something that is to be expected. This kind of forms a normal distribution, right? So what happens if we change the number of coins? Well, let's take a look at that. Here we're going to say, you know what, let's flip 5 coins and see what the distribution looks like. So here you can see 0, here you can see 5, you can see it was really uncommon, and you can see this graph starts to show up. Okay, let's try it again. Let's make it, what if we flip 20 coins? What's the distribution look like there? Look at that. Okay, really low, really low, really low. Then we start to get some. So you can see here we get this nice bell curve of a distribution that really indicates, how a normal function would exist if we were to flip that many coins. So out of 1 million coin flips, we only got 2 where all 20 were heads, and we got 0 where all coin flips were tails. So, I mean, and that's about right. I mean, if you think about it, what are the chances of flipping 20 coins and all of them being heads or tails? It's really, really low, right? And it should be the most common that about half of them were heads and about half of them were tails. So, so this is kind of cool how you can play with the numbers and use this as to kind of experiment.